Intermolecular forces. This is a brief introduction into intermolecular forces, which, if you go on to 152, you will get in a little bit more depth. We will be looking at 4 different intermolecular forces. Intermolecular forces are those attractive forces that hold molecules together in condensed phases. The magnitude and type of the intermolecular forces is basically what determines whether or not a substance will be a gas, a liquid, or a solid. For example, nonpolar molecules tend to be gases. Occasionally they are liquids, and rarely they are solids. Highly polar molecules may either be liquids or solids. Van der Waals forces are intermolecular forces that act between atoms or molecules of a pure substance. There are actually 3 types of van der Waals forces. We will start with the one of intermediate strength, which are dipole-dipole interactions. These are attractive forces that act between polar molecules. As they get more and more polar, the attractive forces increase. In the liquid phase, the positive ends of the molecule are attracted to the negative ends of the next molecule, resulting in a condensed phase most often. In the solid, now they get organized in such a way that the molecules can't move past each other. This table shows several compounds and their dipole moments and their relative boiling points. Propane basically does not have a dipole moment. All of its bonds are nonpolar, and its boiling point is minus 42 degrees Celsius. Dimethyl ether is polar because it has an oxygen in the middle. That's this molecule down here. The boiling point minus 25. Methyl chloride is right here. It has a chlorine on the end of it. It has a fairly high dipole, boiling point minus 24. Acetaldehyde is down here. As you can see, it has a double bonded oxygen on it. The result is in a fairly large dipole of 2.7, and the boiling point is now 21 degrees Celsius. And then finally acetonitrile. This molecule over here has oxygen on it, and the result is a boiling point of 82 degrees Celsius. Hydrogen bonding is a special type of dipole-dipole interaction. Hydrogen bonding only occurs in a molecule that contains small, highly electronegative atoms such as nitrogen, oxygen, and fluorine. Hydrogen bonding is a type of van der Waals force. However, it can also occur in mixtures as well as in pure substances. In this picture we see hydrogen fluoride. The fluorine is highly electronegative, and the hydrogens are basically shared between the 2 fluorines, and the result is a tighter bond and higher boiling points than what we would expect to see. This graph shows the effect of hydrogen bonding. Methane down here has a carbon. It is not highly electronegative, and as a result it has an extremely low boiling point. Ammonia, hydrogen fluoride, and water are those 3 pure substances that have hydrogen bonding, and you'll note that they have increasing boiling points as we go up. The special characteristics of water is that it can form two hydrogen bonds between each set of molecules, whereas hydrogen fluoride and ammonia can only form one hydrogen bond. Then you'll note here that we end up with trends that look like they might have some effect as we go down the periodic table. But if we had followed, let's say, this line with hydrogen sulfide, hydrogen selenide, if we had followed that back to where it would have been, water would have had a boiling point down here of about minus 90 or so if it had followed the trend. So it is definitely showing effects of the hydrogen bonding. To account for that trend that we saw from the hydrogen sulfide to the hydrogen selenide to the hydrogen telluride, we're going to talk about dispersion forces, or London dispersion forces. These result from attractions created by instantaneous dipoles of non-molar polar molecules, or basically the more electrons that you have, the more likely you are to form an instantaneous dipole. This instantaneous dipole then spreads through the substance, creating what are called induced dipoles. So these are the instantaneous dipoles, and they spread the dipoles into something called induced dipoles. The result of that is we can actually get a condensed phase in a nonpolar molecule like bromine because of the high number of electrons in it. Or the other thing that we see is that as we go down the periodic table, boiling points and melting points tend to go up because of the increasing number of electrons and the increasing possibility of having these instantaneous dipoles in a molecule. So here's that trend. As I indicated, bromine is a liquid at room temperature with a boiling point of 59 degrees, and iodine, molar mass, is considerably higher than that of bromine, has a boiling point of 84, and is a solid at room temperature. So what kind of intermolecular forces exist? Let's look at a few molecules. This first one is called normal pentane. It only has nonpolar bonds. It doesn't have any highly electronegative atoms like oxygen, nitrogen, or fluorine. So it doesn't have polar bonds, so we don't have dipole-dipole interactions. It doesn't have hydrogen bonding. So all we're left with are dispersion forces. The molecule below is ethanol. This compound is polar because we have a carbon-oxygen bond and an oxygen-hydrogen bond. This creates the polarity. It also contains a hydrogen attached to an oxygen, oxygens being one of those three highly electronegative, so it also has hydrogen bonding. So as we note here, dipole-dipole, hydrogen bonding. Also point out every molecule, because it has electrons in it, has the possibility of having an instantaneous dipole. As a result, dispersion forces. The last intermolecular forces we'll look at are ion-dipole interactions. These aren't the strongest of intermolecular forces, but they're the strongest we are going to look at in this section. Ions will be attracted toward polar molecules in a solution, especially in aqueous solutions, because water is highly polar. The cations will tend to be attracted to the oxygen in a water molecule, as we see here with sodium and magnesium, anions would actually tend to be more attracted to the hydrogen in chlorine, for example. The other thing that we'll see is that the higher the charge, here's magnesium, has a greater charge, the stronger the interaction that will occur. And this concludes our look at intermolecular forces. The strongest of all four forces is the ion-dipole interaction. Then there are the three van der Waals forces in increasing order of strength. Dispersion forces, the weakest. Dipole-dipole interactions, intermediate. And hydrogen bonding, the strongest of the van der Waals forces.